Muy buenos días a todas y a todos. Estamos dándoles la bienvenida a este seminario sobre ozono troposférico persistente en ciudades, el día de hoy, 30 de julio de 2026. Tenemos una agenda muy completa y muy interesante. Entonces, para iniciar, vamos a darle la palabra al doctor Oscar Peralta, coordinador general de Laboratorios de Energía sobre Contaminación y Salud Ambiental del Canal de Ecología y Cambio Climático. Oscar.
Gracias, Ramiro. Bueno, buenos días todas, todos. Me alegra y que hayan podido darse de tiempo para presentar y presenciar este taller. En este grupo, en este primer bloque, daremos primero la palabra al doctor Germán Ruiz, el director general de Fomento y Desempeño Urbano Ambiental de Semarnat, quien les dará un saludo. Adelante.
Muchas gracias, Oscar.
Thank you, Oscar. Good morning, every one of you. Good afternoon on the other side of the world. On behalf of Dr. José Luis Amaniego, Subsecretary for Sustainable Development and Circular Economy, sending regards. He was not able to make it for this workshop because of other commitments, but he has asked me to convey all the best for this event, which is being held with the participation of all of you. Also, happy to welcome Dr. of the Megalopolis, José Abraham Ortiz, Director General of INEC, Dr. Beatriz Cárdenas González from the World Resources Institute, Luisa Molina, and all the specialists, representatives, government representatives, civil society, national and international representatives at this workshop. Tropospheric ozone is one of the most complex atmospheric pollutants. It depends on photochemical and emissions from transport industry, energy sector, and other activities from human development. Plus, climate change increases the conditions for episodes of high concentrations of ozone. From Semarnat, we strengthen a policy based on science between three levels, tiers of government. Our government advances in contributions, national determined contributions, which are aligned with Paris Agreement, and also promoting mitigation with more resilient chains. And this is our roadmap to have a roadmap to development with a more resilient economy. Improving this will bring better results in public health, and it also contributes to meeting our climate commitments. In this sense, I would like to mention to you all that the Intersecretarial Commission for Climate Change, changed by the Subsecretary Secretary for Environment, Alicia Bárcena, recently approved the 2026-2030 Climate Change Program. This program, known as PEC, is the roadmap that will lead climate action of Mexican government during this administration, and without any doubt, it will continue with climate commitments of Mexico in goals, actions, budgets, indicators, and it will also lead actions of all the key players involved in this important climate action. International experience shows that the most successful experiences combine effective governance, policies, and follow-up. No country on its own may be able to face these challenges on their own. Equality, climate change, sustainable mobility, energy transition, man waste management, and circular economy are a part of the same agenda of transformation. At the Subsecretary for Sustainable Development and Circular Economy, we are working together with INEC, CAME, and WRI to make this space possible with specialists from different countries and regions. At Semarnat, we are convinced that this transition needs to be built from cities. Improving air quality means protecting people's health, strengthening climate resiliency, and promoting innovation, sustainable mobility, energy efficiency, and well-being. We know that around 80% live in cities. As the Secretary Alicia Bárcena has said, ecology transition is an opportunity to build a more just, resilient, and prosperous development model with a humanistic policy focusing on people, promoted by Claudia Sheinbaum. All the best of success at these sessions, workshops, and I wish you every success and for you to get plenty of knowledge and a great exchange. Thanks, everyone. Thank you. Now we will pass the floor to José Abraham Ortiz, Director General of the National Institute of Ecology and Climate Change. Good morning. Can you hear me? Yes.
Luego tengo problemas con el audio. Muy buenos días. Muchas gracias.
Good morning, everyone.
Oscar Peralta.
Thank you, Dr. Oscar Peralta. On behalf of the National Institute of Ecology and Climate Change, I'm pleased to welcome you to this event on tropospheric ozone. It is important we continue with these efforts, as Dr. Ruiz has said, and it continues to be one of the most complex challenges for air quality management and climate change. It is important for these conversations with technical and institutional collaboration. It is important to mention that it is considered as a super contaminant, and as mentioned before, it is an interaction of air quality and climate change. The agenda for this seminar is very important, with exactly reflecting the knowledge and challenges. We know that tropospheric ozone have effects on human health and ecosystems. Therefore, it is important to underline that experiences like Mexico City and other cities like LA will have this opportunity of designing better and more efficient responses. From our institute, bringing across all the scientific evidence is important. Today, with Oscar Peralta, who has been introduced as the new coordinator for contamination and environmental health, he will be dealing with these subjects, and this will produce information to feed decision-making, which is central to the work being done in policies, both in cities and working with climate policies. Facing ozone pollution requires a very important thing that we are lacking right now around the country. And I think the same thing happens around the world. Monitoring. It is important to mention that monitoring is in a crisis, but not so much in terms of equipment, but the very infrastructure and local capacities in order to sustain the country's capacity for analysis and monitoring. It is important for all this knowledge be available in public policy, which is not something being done, and we are pushing it from INEC. So that is to say, producing information for the right decision making based on data produced by science. This is very important because with this we can evaluate situation and we see what we need to improve. By improving our conditions, it is a challenge also mentioned by Dr. Ruiz, and it goes to protecting human health and ecosystems. I want to thank the Ministry of the Environment and Natural Resources, Dr. José Luis Amaniego, who is with us today, the head of the ministry, Alicia Bárcena, who is really working on this, the National Commission of the Megalopolis, through Dr. Hugo Parra, Páramo, WRI Institute. Thanks to Dr. Beatriz Cárdenas for all these efforts to organize this seminar, as well as all institutions and specialists who have made this possible. I trust that this will strengthen capacities and actions of Mexico to improve air quality. Thank you. Welcome. Thank you, Dr. Rodriguez. At this time, I will pass the floor to Dr. Beatriz Cárdenas, Director of UNA Atmósfera and the World Resources Institute. Good morning, everyone. Good afternoon for those of you in other time zones. Thanks, everyone, for being here this morning and share your knowledge, because I'm sure we will be hearing very good information on tropospheric ozone from the World Resources Institute. Tropospheric ozone for us has been of importance. We have heard because of its effects on human health, its effects on ecosystems and nature, and in agriculture too, and also due to its contribution to global warming. As you will see, the agenda was carefully curated with all these ideas to bring together scientific evidence, public policy, but also the work of civil society organizations. And so from this position, I want to say welcome. And as you can see, there is a lot to share and a lot to listen to. Thank you, Dr. Cárdenas. And lastly, Dr. Víctor Hugo Páramo. He is the executive coordinator of the environment mission of the megalopolis. Thank you. Thanks, everyone who are present on the seminar on persistent ozone in cities. First of all, I want to thank Dr. Germán Ruiz, representing Dr. José Luis Samaniego, INEC, and WRI. Abraham, thank you. Thank you for accepting to co-organize this meeting, which will certainly give us a clear overview of what's going on in cities in Mexico and in the world about tropospheric ozone, basically present where we have human settlements. I want to thank too our speakers who have accepted to share their knowledge and experience on this, and of course those who will be moderating sessions. At this time, I would like to welcome the advising committee of the citizens advisors from CAME and our connections with governments who make it up. So I want to thank representatives of the media too. And also I want to welcome representatives of cities in Mexico and from other parts of the world. As most of you know, CAME is a partnership of all 7 states in the center of Mexico, and our goal is to harmonize environmental policies in the region. This region is made up by Mexico City, the state of Mexico, Hidalgo, Puebla, Morelos, Querétaro, and Tlaxcala. It's above directions, above the environment, health, agrarian and development and infrastructure federal secretaries sit at this meeting, at this organization too. And our central objective is precisely to oversee air quality. Megalopolis is a region with 30 million inhabitants, and most of it Mexico City and the conurbation with over 23 million inhabitants, 1,450 factories, and several million vehicles. In this metropolitan area, ozone is one of the contaminants of highest concern, as Dr. Cárdenas has mentioned, due to its negative effects on public health and on other components of ecosystems. By the end of the 80s, we saw an environmental crisis of air quality. Back in those days, all contaminants were present at extremely high levels. This crisis resulted in programs to improve air quality. And the first one started in 1990, and today the ProAire 2030 is still operating. And for each of them, we have seen improvement actions. And by between 1990 and 2025, we have seen reductions of almost 92%, nitrogen dioxide 42%, sulfur dioxide 8%. In spite of these improvements, right now in the metropolitan area of Mexico City, we don't see a sustained reduction of the tropospheric ozone, this in spite of continued implementation of measures of priority. Science reports, cities from Mexico and the world point at similar situations and the possible reasons behind this behavior. And that is precisely why we invited these experts who we have in the room today in order to know firsthand what their experiences, causes that identify, and also how this situation has modified air quality situation. And we hope this seminar will help us identify the causes making persistent ozone one of the priority concerns around the world. And with this, to help determine what are the right public policies for this control, as we said before, to benefit public health in our cities, as well as implementation and adaptation to climate change. So welcome, and we wish this seminar will help us meet these objectives. Thank you, Dr. Páramo. And lastly, Dr. Luisa Molina, the founder of...
Welcome, Luisa.
Welcome, Luisa.
Okay, I think you can see me, right? Well, buenos días a todos y todas. Good morning, distinguished guests, colleagues, and friends. First of all, I want to thank the organizers inviting me to give the introductory remarks. Our shared goal for the seminar today is to raise awareness of the persistent ozone problems as both an environmental and global public health, to better understand the current state of ozone pollution in some cities, and to share experiences regarding effective pollution reduction strategies. Next slide, please. Siguiente, por favor. Urban air quality is strongly influenced by several factors, including geographical location. I think, did it go the next slide? Yeah, okay. Urban air quality is strongly influenced by several factors, including geographical location, demography, the meteorology, atmospheric processes, and the level of industrialization and socioeconomic development. Rapid growth in urban population and increased energy demand have generated large amount of pollutant emissions that degrade air quality, threatening human health and ecosystem. Some pollution control decisions are simple. As for example, in 1952, exposure to smoke from sulfur-rich coal caused severe illness and death during weak weather-induced pollution episodes in London. While switching to low sulfur fuel improved air quality, coal-burning power plants remain major contributors of sulfur dioxide and coal-emitted pollutants in some regions. Since Dr. Hagen-Smith identified ozone as a major component of photochemical smog in 1950s in Los Angeles, high ozone levels now affect many cities all worldwide. Despite the widespread adoption of California's pioneering emission controls, regulating urban ozone remains difficult. As shown, on the other hand, global COVID-19 lockdown measures demonstrated that aggressive emission reduction strategies can successfully improve urban air quality. In fact, many cities achieved unprecedented declines in air pollution. As shown in the photograph here, in Delhi, one of the largest megacities of the world, and most polluted megacities, in fact, experienced the clearest sky in years as pollution dropped to its lowest level in 3 decades because of a strict lockdown. However, pollution has returned after the lockdown was lifted. Next slide, please. So emissions around the world come from a mix of natural processes and human activities. Many pollution sources emit multiple pollutants, including harmful pollutants such as black carbon, carbon monoxide, nitrogen oxides, sulfur dioxide, and volatile organic compounds, as well as greenhouse gases such as methane, nitrous oxide, and carbon dioxide. The emitted species can undergo complex series of chemical reactions, forming secondary pollutants. For example, nitrogen oxides and volatile organic compounds react in the presence of sunlight to produce ozone and other oxidants. These reactions also generate secondary particles. Volatile organic compounds and nitrogen oxides are emitted into the atmosphere by both anthropogenic and natural sources. The consumption of fossil fuel for motor vehicles, industry, power generation, and residential activities are the major emission sources of both precursor pollutants. The use of biomass for domestic heating and cooking also emits VOCs and NOx. Vegetation is also a major source of reactive VOCs. At the regional scale, wildfires are important sources of VOCs and NOx, especially in seasonal fire-prone regions, as is happening now all over many regions around the world. On a global scale, nitrogen oxides and volatile organic compounds, carbon monoxide and methane drive ozone production. In urban areas and downwind regions, ozone formation is mostly driven by local NOx and VOCs emission. So the main driving forces of surface ozone formation are the interaction of sunlight-driven photochemistry, nitrogen oxides and volatile organic compounds, and meteorological conditions that control reaction rates, pollutant transport, and atmospheric stability. Understanding and managing both emission sources and meteorological drivers is key to mitigating ozone pollution. As mentioned before, particulate matter is co-emitted in the formation of ozone. Recent research shows that changes in particle formation, especially PM2.5, can also influence ozone chemistry. Therefore, ozone control measures must consider the combined effect of both precursor pollutants in the formation of ozone and particles. Now, ozone plays a dual role as harmful pollutant and as a powerful greenhouse gas. Ozone, methane, and black carbon are major short-lived climate forcers, taking as action to reduce both yields immediate rapid cooling benefits. Coordinated control strategies targeting both ozone pollution and climate change can simultaneously deliver better air quality, improve human health and ecosystems, mitigate climate change impacts, as well as reduce social costs and regulatory burdens. Next slide, please. La siguiente, por favor. Next slide, please. Up. Okay. Ground level ozone plays an important role in atmospheric chemistry by controlling the oxidation potentials of the atmosphere, posing risks to public health and damaging vegetation and crops. The damages from ground level ozone exposure have resulted in significant economic losses across human health, agriculture, and material. While ozone has a relatively short atmospheric lifetime, typically hours in polluted urban regions, its lifetime in the free troposphere is of the order of several weeks, which is sufficiently long for it to be transported over intercontinental scale and may influence air quality on hemispheric scale. In such a context, ground level ozone has been the subject of scientific research and air quality management for several decades, with policies and monitoring programs covering urban, regional, and hemispheric scale. Now, sorry? Improvement in scientific knowledge to measure pollutants both in the laboratory and in the field, along with the development of sophisticated air quality models, have led to better understanding of emission sources, atmospheric processes causing ozone episodes, and effective control strategies. Pollutant emission from vehicles and industrial activities have been reduced in many cities by applying technology forcing policies, cleaner fuel, stricter environmental regulations, and economic incentives. However, despite substantial reduction in key precursor pollutions directly emitted into the atmosphere, some cities have made little or no progress in lowering surface ozone level over the past 10 to 20 years. As an example, the graph shows the air quality trends in the Mexico City metropolitan area. Mexico City air pollution problem was considered among the worst in the world in the 1980s, when the newly established Air Quality Monitoring Network revealed ozone concentration about 300 parts per billion many days a year. However, after 3 decades of implementing successive comprehensive air quality improvement programs, Mexico City has made significant progress in improving air quality and is a role model for many cities and emerging megacities. Now, no improvement in ozone concentration has been observed since around 2010, but Mexico City is not alone in struggling to reduce ozone. Some other cities are experiencing similar challenge. So we need to understand why ozone concentrations have not decreased in some cities, and how should environmental policy adapt to this complexity? Next slide, please. La siguiente, por favor. So tropospheric ozone is not emitted directly into the atmosphere. Instead, a complex mix of precursors, emission sources, meteorological conditions, and atmospheric chemistry makes it difficult to control. Managing persistent ozone pollution will require shifting from localized emission control to a holistic, multifaceted, and comprehensive strategy. This approach will take into consideration the growing urbanization, evolving emission sources, climate-induced extreme events such as heat waves and wildfires, and transboundary pollution to ensure sustained air quality improvements. Overcoming ozone climate and health challenges will require cutting-edge interdisciplinary research, evidence-based intersectoral policy and actions from decision makers, and active engagement from stakeholders and the public. Now, in such a context today, the Ministry of Environment and Natural Resources, the Environmental Commission of the Megalopolis, the National Institute of Ecology and Climate Change, and World Resources Institute of Mexico jointly organized this webinar and invited national, international, scientific, technical, and policy experts and decision makers to share their experience regarding the current state of ozone pollution and the proven air quality management policies in their cities and regions, as well as experts on the impacts of ozone on health and ecosystems. Now, international collaboration is vital for sharing scientific knowledge, data, and capacity development. The current wildfire ranging across many regions around the world and the transboundary transport of pollutants make it even more pressing for international collaboration. Air pollution has no boundaries because the atmosphere connects all of us, all regions around the world. So effective solutions need both local action and global cooperation to achieve cleaner air and a healthy environment for all. Well, thank you very much for your attention.
Thank you very much, Luisa. Muchas gracias a todos los que participaron. Quiero agradecer especialmente a la doctora
Thank you,
Luisa
everybody
Molina.
who participated, especially Dr. Luisa Molina, who is a member of the Advising Scientific Committee, and it has been paramount to let us be in contact with all the speakers and let us put together this seminar. Thank you very much, Luisa. Now, let me introduce myself. My name is Ramiro Barrios. I am in the Environmental Commission of the Megalopolis. I will be the general moderator for today's session, and I will pass the floor to Dr. Luisa, who is the head researcher of the Atmosphere and Climate Change Research Institute of National Autonomous University of Mexico. She will be leading this session. Go ahead, please, Doctor. Thank you very much, Ramiro. Good morning, everyone. Welcome, everybody who are present in this meeting. In this session, we will talk about some scientific finding after some atmospheric observation and forecast of impact on health, on public health. We have 4 very good presenters, and I would like to remind them that for each of their presentations, they have 15 minutes in total, and they will be notified 3 minutes before the presentation is over. So our first presenter is Dr. Johan Sun, who will talk to us about problems of ozone in Chinese cities. And let me introduce the doctor briefly. He is a professor at the Peking University in China, member of the Control Committee of Ozone Damages in China and Environmental Sciences. His research is focused on the formation, effects and control of environmental pollution, complex at urban and regional levels, with oxidative capacity of the atmosphere as a key subject. He has made many advances in understanding the quantitative mechanisms of the zone and the particles. He has also developed regional systems of pollution control that have served as a basis for the application in the long term of the Changyu and the Delta River, and he led the creation of a monitoring network for the research on toxic fog in Peking 2020. He also started the suspension network in China and created the Committee Control of Ozone Pollution, and he is contributing actively in efficient control measures at national level. Dr. Yang, the floor is yours.
Okay, so hello everyone. This is Keding Lu speaking. So I'm presenting this talk on behalf of Yuan Han, so who has other things to do tonight. My presentation includes 3 parts. Okay, what's happened? It brought automatically. Can you control?
Regresar al inicio, por favor.
Yeah, so yeah, please go to next page. So my presentation includes 3 parts. First is the air quality progress in China. So I would like to introduce the 5 decades of pollution control and the current rapid PM2.5 improvement. Next page. So here is a roadmap. So you say, similar to what happened probably in Mexico City. So we first control in SO2, total suspended particles, and focused on acid rain. And then this is focused on industry pollution. Press the button. Please press the button. Okay, then in year 2000, so haze is a problem in China and also in Asian cities. And in this case, we include the control of PM10, and in this case. Next, press the button. Okay, so in 2010, in this time that we have a maximum PM2.5 pollution, and then we focused on the NOx control, mainly by the power generator. Yeah, this is a map to show in 2010 that we have a lot of PM2.5 pollution days for Chinese cities. Press the button. Okay, you say that after since 2013, that when we focused on the PM2.5 control, so basically we move from the total emission control from the air quality control by PM2.5 concentrations. Then that drives a rapid decrease of PM2.5 on the national scale and also more obviously at regional scale, especially for the Beijing and surrounding areas. so which the reduction reaches 25%. And actually the effect is maximized nowadays. So we have blue skies almost many of the times. Press the button. Okay, so now we go to a next phase that we do joint control of PM2.5 and ozone. And so we move from single pollutant control to multi-pollutants control in China. Next page. And this is a remarkable air quality improvements in recent years, as you can see from this map. So PM concentrations reduced continuously since year 2000. And this is driven by the reduction of SO2 and also the reduction of NOx. Press the button. Okay, you say in 10 years, PM2.5 dropped down by 44%, and that is driven by 68% reduction of SO2 and also 37% reduction of NO2. Press the button. So the heavy pollution days, if we compare 2024 to 2015, actually, the whole state reduced 65%. And in the Beijing and surrounding areas, it reduced by 9%. So this is remarkable. So it's from 43 days to 2 days per year now. So almost no pollution days now. Okay, so it's realized basically in China, the blue sky is ever present and the stars twinkle. Next page. Okay, so the air quality progress is good, but we suffered persistent ozone problems like the other place of the world. So this is a map that we basically have heavy ozone pollutions in the BTH area, the Beijing and Shanghai and this North China Plain in between. So it increased a little bit in the beginning and now it started to decrease also. And we believe it's anthropogenic emissions are the main driver of the observed ozone increase. Press the button. And you say this high concentrations are comparable to what in California and also in Mexico City in the spatial comparison. At the maximum pollution episode in China. Okay, press the button. Next page. Next page. Okay, here you see the variations. You rarely observe these two phases. So before 2020, it's mainly increase. And after 2020, some cities started to decrease and some cities still increase. And basically, we could conclude that the national average MDA8, so this is daily averaged, so daily maximum 8 hours ozone concentrations increased before 2020 and followed by a high level fluctuations after 2020. Next page. And it's not only the high concentrations, it's also the pollution that also expands in spatial size, specifically in the two hot years, 2019 and 2020. And then we observed a large-scale ozone pollutions. So the ozone exceedance more than 85 cities. In 2019 and 2020 are more than 20 days. So this is serious. And of course, somehow last year it is good. And this year we are hot And here is, I compare this concentrations to United States and Mexico City. And then we say, okay, actually, at the beginning, 2018, we are much higher than, or slightly higher than Los Angeles, but much smaller than Mexico City. And nowadays, we are comparable to Los Angeles and much less than Mexico City. So it's in general, the problem in China also faced in North America. So maybe there are good values to learn from each other. Next page. And the difficulties is for the country like China or like US or maybe Mexico too, that the North will say nonlinearity vary a lot from North China, from Eastern China, South China, and Western China. So it is not possible to have the one-size-fits-all control policy possible or risky. Next page. And this is from the satellite, we can say actually in the high ozone pollution space, then it's more, we'll say, controlled. But in the other place of the country, it is more NOx control. So this makes the control policy more complicated. Next page. And this is a control strategies. You say in China, we first control SO2, and then control the direct emission of PM2.5, and then the control of NOx. And now we recognize, okay, actually the high ozone value place, North China Plain, are controlled more by VOC. So we now start to control VOCs, specifically after 2020. Next, press the button. Press the button. Press the button 2. Okay, you say Zambian concentrations. So basically, we the control policy from China is switch from or evolves from the SO2 and NOx and dust control to the co-control of VOC and NOx. So actually, very similar to what happened in US and Mexico, I would say. Press the button. Press the button. Okay, so actually we compare to that, that is similar to what happened in US. Okay, press the button. Then I want to explain what we have done from the science. So what we have learned from the science part in China, briefly. So to explore or to support the control policies, actually we have done a lot in China. Please press the button. Okay, we established a 3D monitoring and ensemble forecast system that includes supersite measurement to explore the formation mechanism, to establish the inventory and also models to make the capacity of prediction and also for control scenarios. Okay, then
we have 3 minutes left. Getting 3 minutes left.
Okay, so it's close, come to the end. Next page. Okay, so this is done because China is so large. So we have performed many regional integrated fed experiments in China. So we probably have collected so far the most rich databases worldwide to do this ozone PM2.5 and also centered on atmospheric oxidation capacity measurement. And for this, we know really how the ozone is formed and also PM2.5. Press the button. Next page. Okay, we found, okay, why? Actually, there are magic mechanisms to support strong atmospheric oxidation capacities across diverse environment in China. And we uncovering novel radical sources from no-NOx to high-NOx regime. And that is the reason actually why I would say we have persistent ozone pollutions and would be the same for US and Mexico City. Next page. And this enhanced oxidations we found a partially offset reduction in PM 2.5 precursors. So we reduce a lot SO2 and NO2. But nowadays, we found a less and less PM 2.5 decreasing because it is more and more secondary PM 2.5. And then we have the strong oxidations. So nowadays, we enhanced persistent ozone challenges and also PM 2.5 phase reduction. Next page. And we found actually the importance of O VOCs and SI VOCs. So you say in this graph, O VOCs are actually comparable importance of the PALM's VOCs. And SI VOC would be important also for SOA. Next page. And we have actually achieved VOC reductions in 2 large cities in China, that is Beijing and Shanghai. So we have then successful scenarios. So we probably can continue or apply that to other cities. And we hope then we obtain ozone reduction in future period. Next page. And these control policies are also supported by this diagnosis by OBM, so observation-based models and also the air quality models, so which can support the precise control of VOC or NOx. Next page. And this is a scenario in a case for Chengdu and surrounding sites when we make a lot of controls for NOx and VOCs in the meantime, and we rarely reduce ozone for the FASO World University Games. So this reduction of NOx and VOC is observed, and also we observed ozone. So that's really proof that ozone can be controlled even in short period. So that's successful cases and also a large experiment. Next page. So the government in China has set a new target. So we will have PM 2.5, the annual average is lower than 25 microgram per cubic meter. That is annual average. So in summer, it's basically lower than 10 microgram per cubic meter. It's similar to US. And then the ozone is in decreasing too, we expect in the near future. Okay, next page. So here is the end. This is 3 takeaway messages for you that ozone is a problem that China treats seriously. So we have control policies that we do focused on VOCs for short term and also NOx for long term. And also this will be accelerated, specifically benefit from carbon neutrality policies in China. So our experience showed that we may control ozone for this huge country and for this megacity areas. And we hope what we have learned can be transmitted to Mexico City and also other developing countries. So this is based on contact in the future. Okay, that's the end of the presentations. Thank you.
Thank you, Dr. Sang. We appreciate your presentation and le damos la bienvenida a la doctora Laura Gallardo.
And now we welcome Dr. Laura Gallardo, who will tell us about the atmospheric observations in terms of tropospheric ozone. She is the head professor at the Chilean University, and her research is on atmospheric processes, regional scales with the accumulated nitrogen cycle, tropospheric ozone, and short-term precursors. At the same time, she studies air quality in megacities. In 2024, she was distinguished as a valid member of in science advancements. Thank you for your presentation. Let me remind you that you have 15 minutes. I will tell you 3 minutes before the presentation is supposed to end. Go ahead, doctor. Good morning, everyone. Good morning. For me, it is a pleasure to share with you. Speaking to you from the south, and yes, thank you very much for the opportunity to share with you. I will do my best to speak in a standard Spanish so that the English translator does not find it too hard. I will not speak in a very Chilean language, but it might slip from time to time. Next slide, please. Let me tell you about the group of experts on reactive gases of the Global Atmospheric Watch by the Meteorological World Organization. By the way, I have the pleasure and honor to partake in that group of experts. And then I will go over very briefly, because the previous speakers have already represented it, about ozone and its impacts, which are so many. And they go way beyond that. They go way beyond just air quality. And then I will show you some results about central Chile. And of course, for many, many years have faced a major ozone problems. Next slide. With the Meteorological World Organization, since the 90s. Can you not hear me? Yeah, I think. Yeah, we can hear you well in Spanish. Yeah, anyway, in the 90s, there was a global monitoring network of the atmospheric composition that was created, and the idea was to keep track of how the atmospheric composition was changing. And from this network called GOW, the GAW, Global Atmospheric Watch, a series of group of experts was established, and amongst them one specializing on reactive gases, but mainly focused on tropospheric ozone and its precursors, hence nitrogen oxides, carbon monoxide, and other volatile organic compounds, as well as sulfur dioxide. And because of the importance that they have, both in terms of air quality as the effects they have on the weather, climate, they have a huge impact on vegetation and agricultural activities. Next one, please. This map over here shows that this is kind of a weird map, because the northern hemisphere is larger than it used to be, and then the equator is not exactly halfway at the map, but it shows mainly the distribution of stations that this monitoring network has, the GAW network. It is pretty evident that they are mainly focused in the northern hemisphere in Europe, and like it happens every time in the southern hemisphere or in the global south, the distribution is rather scarce, it's rather thin when it comes to monitoring stations. Among them, I will rule out a couple of them pointed out with the arrows, corresponding with 2 stations in Chile since 1995, more or less. And I'm talking about the Tololo station and the Rapa Nui station, or the Pascua Island, as we like to call it, where in Tololo they carry out systematic measures of ozone, and we have been doing so for a long time. At Rapa Nui, with all of these stations, they have some are better equipped than others, but they have contributions from over 100 countries. There are many stations with different levels of sophistication. And these stations basically were supposed to monitor how the atmospheric composition is changing. Now, why is ozone interesting? Maybe everybody here has a lot of answers to that, but one of them is one of the main drivers of climate change, and it exerts a lot of pressure on our climate change, since it exerts around 1 or 2 watts per square meters, and then methane that has like 0.60 something watts per square meter, and tropospheric ozone that, according to the last forecast of the interclimate panel, with 0.47, but with a very wide uncertainty of more or less 0.23, that is to say 50% of uncertainty, and that is due to the absence of observation. There isn't enough observation in the middle troposphere, and especially in the southern hemisphere. Just like I said before, ozone has to do with the presence of radical hydroxyl, and it is determining for the oxidation of the atmosphere, and in excess we know that it has a huge impact on public health and vegetation, including agricultural activity. And there is some climate coupling that has to do with the fact that ozone in vegetation ends up hindering carbon sequestering, and that hinders the carbon cycle in and of itself. Here you can see some results about the situation of ozone in central Chile. You know that Chile is a very long country, but also quite wide, because Rapa Nui belongs to Chile, and that is a 5-hour flight from the capital, from Santiago. But taking a look at central Chile, 36 degrees to the south is where most of the population is concentrated. And there in the northern part, we have Tololo Mountain, which gives us a good condition of the depths of central Chile, and the condition previous to Chileans putting many things in the air and changing its composition. We have everything we have coming from the other side of the Pacific, and that is something we can measure and we can determine in Tololo's case. What you can see on the right-hand side is a timeline with ozone as a monthly average in this station, which very interestingly is in the free troposphere, in a very complex area, because we have the Andes mountain as well at 2,000 meters above the limit layer. And the available data we have from 1995 and 2004 showed that, first of all, there were many changes in terms of concentration or ozone mixes, but after 2006, 2007, more or less, it started to go up. The studies we have carried out based on some statistical techniques, rather advanced ones, we have been able to determine that that what predominates here is methane. Unfortunately, methane hasn't been systematically measured as the ozone. This methane series is basically the Rapa Nui one, but with a period when we had access to instruments that allowed us to measure methane. And once again, on the right-hand side, you can see the changes in the trend, in the methane trends. Coincidentally, this is not direct. However, if we don't take into consideration methane changes, it is very hard to reproduce the changes in the ozone that we are seeing. These changes in ozone that we're seeing since 2006, 2.1, 0.8 ppb per decade, which for a deep area, a clean area, is a major ratio. More details about that can be found in those references. But let's go to see some cities. Next one, please. Here's a trend of ozone trends and timelines, and ozone trends and its changes in a station in the western area of Santiago, the city that nowadays has around 8 million inhabitants, not yet a mega city, but in terms of pollution, we definitely rank as a mega city. And we have these values, these ozone values, which are maximum, where it reaches its highest point in summertime. Unlike Tololo, which has maximum points more associated to the burning of biomass in September, October, and November, mainly from the other side of the Pacific, more than from South America. However, Santiago has highest points during summer with a higher photochemical activity. Below you can see the trend. There are two change points, one around 2004 with a broad range of uncertainty, and another one more or less in 2016, around 2016. And this is because of a couple of things. On the one hand, the downward trend that we were seeing at the beginning of the 90s, which is probably associated to it. This is a period of massive growth, economic growth. A lot of vehicles were being bought, and nitrogen dioxide levels started to go up. And then a period without many changes, but since 2016, as I said, the trend has been going up, and this change in growth is starkly marked in the maximum levels than in the means and in the average. At the 5 and 95 percentiles, which are pointed out with yellow lines, show that most of these events have been associated to other events coming from climate change, and it has to do with the frequency, the increase in the frequency, intensity, and extension of wildfires that have touched central Chile since 2016. Next one. 3 more minutes, please. Okay, that's great. Another element that has had an influence in Santiago's case is isoprene changes. A few years ago, thanks to a colleague called Rodrigo, who will speak later, we have had instruments that allow us to measure isoprene, which is yet another biogenic VOC, and we see the effect of a massive drought that we had since 2010 to 2022, where this hydric stress phenomenon had changes in the flow of biogenic isoprene, and also some minor changes between the end of 2010 to halfway through the last decade. And maybe it is changing too nowadays. We are looking into it. The observations that you can see and the data you see there are essentially for the analysis, reanalysis. Next one, something else that happens in Chile, especially in central Chile, is that, as you know, we were most of the time under the effects of a high point of the Pacific that is quite persistent and intense. But more often than not, that it is increased in winter and summer, especially summer, and many of our problems caused by particles, which is what happens in winter, are associated to low points at the coasts. We have an equivalent phenomenon in the northern hemisphere and Namibia, etc. Basically, the temperatures are changed, and what you can see there is just for winter, the morning PM 2.5 average and maximum ozone that has an impact on the temperatures. Although we have the maximum ozone levels in summer, in winter, many days, there are days where the ozone models are very high and very open, and that is associated to a secondary formation of air sprays. Next one. In a nutshell, the GOWM has had this network for the past 30 years with a lot of stations, collective information in far-flung areas telling us how the world is changing in general. Some very interesting notes, except from Tololo. Since 2006, they see that they have an upward trend, and it is associated mainly to changes in methane, as it happens in the southern hemisphere. And central Chile, we can see an increase associated, on the one hand, in depth changes in the southern hemisphere, and also to our own anthropic emissions, and also isoprene. And let us not forget about extreme phenomena such as wildfires, and in winter, ozone is also associated to the secondary production of particles. Thank you very much. Thank you, Doctor, for your wonderful presentation. Let us welcome now Dr. Arrington, who will tell us about ozone forecasts. Dr. Parrington is a scientist in atmospheric composition, and he has activities in monitoring services at Copernicus. His work is focused mainly in monitoring the global atmospheric composition and air quality, as well as studying emissions and transportation of pollutants coming from wildfires, sandstorms, and volcano eruptions. The floor is yours, Doctor. I'll let you know when you're 3 minutes away from the end of your presentation. Thank you. Thank you for the presentation. Good morning, everyone. I can speak Spanish, but I think it will be better if I give this presentation in English. Can anyone share my presentation, or can I share my presentation directly?
We have your presentation. 1 minute, please.
Okay, thank you very much. Okay, so thank you to the organizers for organizing this workshop and the invitation to present and to talk about ozone and air quality forecasting that we do in the Copernicus Atmosphere Monitoring Service. And the focus here is going to be more on ozone forecasts for Europe using regional modeling. But please remember, as I'm presenting, that this is also, we also have these similar products at the global scale as well for worldwide coverage. So next slide, please. So just by way of some quick introduction, so CAMS, the Copernicus Atmosphere Monitoring Service, is one of 6 data services provided by the European Union's Copernicus program. And our focus is really on atmospheric composition and the impacts for air quality and health, things like the ozone layer, UV radiation, applications in solar energy, climate forcing, and all of this is quality controlled, fully open access and available data sets and data products. Next slide, please. And so the way we generate our forecasts, we're running 2 systems, essentially a global system using the ECMWF weather forecast system globally. So this includes all the observations for meteorology. It includes all, and we have a version that has all the chemical tendencies, the emissions, sources, and sinks of atmospheric pollutants. And one of the key aspects of this global forecasting is the use of satellite observation. So we're running the model and we're adding in regular constraints on the weather aspects of the model, but also the atmospheric composition aspects. So this is aerosol optical depth, total columns of ozone, carbon monoxide, nitrogen dioxide, and sulfur dioxide. And then on the right-hand side, we have this regional system for Europe, which runs at higher spatial resolution and is based on 11 regional chemistry transport models and calculating an ensemble median of those. And on this side, we take the lateral boundary conditions from our global system, and we also integrate ground-based inputs, so regulatory measurements, in situ measurements of the main air pollutants are assimilated to produce analyses. And at the heart of all this is evaluation and quality control, and I'll mention that again shortly. So next slide, please. So what I'm going to show is really just a fairly general overview of, first of all, our forecasts and analysis in terms of what this means for ozone for Europe. And then we have some policy-related tools, which I'll also touch on as well. So I'm going to start with our forecast here. On the left is an animation of the maximum daily averaged 8-hour surface ozone concentrations for Europe through the second half of June of this year, showing this ozone pollution episode, which crossed many parts of Western and Central Europe during those days. And on the right-hand side is the population-weighted surface ozone for Europe between the 15th and 21st of June. And in this image on the right, I'm picking out the whole domain in the blue colors, but the red lines are perhaps the more interesting for the topic, the themes of this workshop, which is showing the EU 27 capital cities. And this gives the indication, particularly from the 19th to the 21st of June, those daily peak values are really the highest in the capitals in this episode. And at the bottom of this slide, there is a link to where you can access the data from. Next slide, please. So in the next slide, I'll show some aspects of the evaluation that I mentioned earlier. So maybe you need to click again, please. So here. So here, the image on the left is the same as from the previous slide. I think if you click one more time, it might play the animation again. And on the right-hand side is some examples of the evaluation that we can do. And in this case, we're showing the analysis, and maybe it's difficult to see, but the time series is showing the ozone concentrations hour by hour for all European stations on the top left, and just for those stations in Belgium, just as an example below. So the black lines and the gray lines are the observations from the European Environment Agency in situ network, and the orange lines, the thick line is the ensemble median, and there's a spread, if you can make it out, of the 11 CTM. So this shows that last week of June, particularly for Belgium, this very clear increase in surface ozone that persisted for a number of days. And on the right-hand side is just the spread, the scatter of all of the model outputs. If you advance one more, please. And then this is the same, but looking at the MDA8 ozone rather than the hourly concentrations. And these graphics on the right were taken from a server that runs in near real time for the evaluation of our regional products. There is also a global evaluation server where you can compare country by country, station by station, ozone, PM2.5, and various other pollutants over the current season and previous season. So it's a very versatile tool for querying what the CAMS forecast show. And also the link above this EQC reports, we provide on a quarterly basis for the global and regional forecast a validation document, which covers all the main pollutants at the global and European scales. Next slide, please. So if I switch quickly to talk about some of our policy tools, and again, these are just examples, and it shows what examples are possible with this kind of forecast data on the kind of models we're running CAMS. So there are a few different aspects, and I'm just picking out two really. On the left-hand side, and I'm focusing here on Brussels, of course, in Belgium. On the left-hand side are the country contributions, so we can understand how much originates in the country of the city that's selected, but also then in the neighboring countries or across Europe, and also the transboundary and hemispheric aspects. On the right-hand side, then this is the sectoral contributions, so the emissions from the different sectors, plus also, again, natural and hemispheric emissions. And the key point here for Brussels for this episode at the end of June of this year is that the natural and hemispheric sources of ozone were the highest. And so this is common across many cities. And of course, this is, as was previously described, this is a very important aspect of understanding ozone pollution, how it's changing in cities, and being able to characterize the transboundary and long-range transport aspects. Next slide, please. Also, in these tools, we have some applications that can be used to explore the chemical regimes or how emissions changes might affect pollution levels, including ozone. So on the left-hand side is there's a toolbox where you can use these sliders on the left-hand side to reduce the emissions from traffic, industry, residential, agriculture, and the others listed there. All I'm showing here, just as an example, again, for this end of June case 2026, if traffic emissions and industrial emissions were reduced by 10% each, it would have resulted in about a 5 micrograms per meter cube reduction in the ozone daily max, particularly over northern France and the Benelux region. So, and on the right-hand side, then we also have some scenarios where, based on EU regulations and directives, on the scenarios for 2030, if we had these cleaner outlooks in place, what they would mean for a particular pollution episode at the moment. So again, for the same case, with these clean air outlooks, again, there would have been less ozone in the peak of this ozone episode a few weeks ago. Next slide, please. And we're now also looking into augmenting these tools by developing some new applications, which are currently in the prototype stage, but will be implemented in the future. One of these is for better quantifying the contributions to ozone in a particular location, which is shown on the left. And we have similar tools which are then directed at natural dust, which is a big problem for Europe with Saharan dust transport, for example, and also vegetation fires. And these are being designed to be complementary to the official regulatory tools and regulatory agencies, which also monitor air pollution and policy implementation for Europe. Next slide, please. And then if we go back to more the modeling side of things itself, in addition to the forecast analysis, we also have a reanalysis of the European air quality, as well as a global reanalysis. And this is a reanalysis, if you don't know, it's a combination of observations and a consistent modeling system, so we can then compare this year with previous years. I think if you press once, we should see this the image on the left animate. So these are the number of days where the highest 8-hour mean ozone daily 8-hour mean ozone exceeded 120 micrograms between 2014 and 2025. And on the right-hand side, we published a few weeks ago our annual assessment report of European air quality, and this is the images show an example of the progression of ozone pollution during August 2025 using this reanalysis data set, and this report is available by the link below. Next slide, please. And so now we see the animation, so the interannual variability of the days exceedances of the ozone metric across a 10-year period. And of course, this will be updated to 2025 and beyond. Next slide, please. And then just one final aspect on how one aspect of how this data can be accessed. There is a series of thematic hubs that are organized by Copernicus, and one of those is the Copernicus Health Hub, which is highlighted there. This is implemented and run by CAMS, and the idea is it's bringing together the air quality data sets, plus also other health relevant metrics from across the Copernicus services to provide one place where all of these data sets can be accessed and under the theme of health.
You have 3 minutes left.
Thank you. I just have 2 more slides, which are wrapping up. Thank you. So next one, please. So yeah, so just to wrap up, hopefully you've got a sense of how we are forecasting and monitoring ozone pollution as well as general air quality across Europe using our CAMS regional system. In principle, this kind of analysis can be done anywhere in the world, but with our global system, this isn't possible, but we provide this global data could be used in principle to provide boundary conditions for regional models and anywhere in the world and the development of these similar kind of tools. So if anybody isn't already aware and is interested in having more information about CAMS, and particularly in terms of accessing the data, we provide a wide range of help and support. So there is a user forum where anybody can go and ask questions and have more answers perhaps from the community or other people who have encountered the same issues. But then also there is a way of raising tickets and raising issues, or also feedback on what the products are showing in different regions of the world through the help and support app here. And the next slides, just to further enhance this, we also have various training resources that are also open access and free to use. And if there's anybody that's interested in the development of particular training resources in accessing and using the CAMS data, then we're also open to developing those and taking user feedback into developing tools and trainings which are useful for as many users as possible. And so the next slide is just to say muchas gracias. Thank you very much for your attention, and I'll answer any questions in the chat. Thank you.
Thank you, Dr. Mark. Pasamos con nuestro siguiente invitado, que le damos la bienvenida al
Dr. Speaker. Let's welcome Dr. Timothy Buckler, who will be telling us about the ozone modeling for the Gothenburg Protocol. Dr. Timothy, between 2003 and 2011, was a researcher at the Max Planck Institute, where he developed atmosphere chemistry models, and since 2012 he's been leading the research group for the Research Institute for Sustainability Central Helpman in Geoscience in Potsdam, Germany. And since 2017 he's a guest professor of the Berlin Free University, and since 2019 he co-chairs the Hemisphere Transport or Air Contamination. Doctor, go ahead.
Yeah, thank you very much and for the introduction, and thank you for the organizers for inviting me and asking me to come and talk about what is happening with ground level ozone in the Convention on Long-Range Transboundary Air Pollution. Next, please. So just a quick outline. I'll talk briefly about I'll introduce the Convention on Long-Range Transboundary Air Pollution with a brief introduction on the development of international air quality policy, then go on to talk about the Gothenburg Protocol itself, which is the instrument that regulates ground level ozone under the convention. I'll talk a bit about the Task Force on Hemispheric Transport of Air Pollution before moving on to the current revision of the Gothenburg Protocol and with an outlook on how ozone will look in the future version of the Gothenburg Protocol. So next, please. Yeah, so air quality emission sources and so on. Next, yes, thank you. That developed after some years to national air quality legislation. So there are some, for examples of this here, the UK and US Clean Air Act, German and Swiss environmental legislation, for example. But it was pretty clear after a while that this was not enough, that air pollution is not just restricted to national areas, that the atmosphere doesn't know any boundaries. One of the key examples of this that motivated the Convention on Long-Range Transboundary Air Pollution was, of course, acid rain. So the CLRTAP, Convention on Long-Range Transboundary Air Pollution, was the first ever multilateral environmental treaty covering the UNECE region, first established to combat acid rain, but has since expanded to combat other kinds of air pollution, including ozone. Next, please. Oh yeah, and there's the geographical scope of the convention, right? So the convention, like I said, consists of 8 protocols. It began as a framework convention to enable cooperation, develop more protocols over time, beginning with the protocols on sulfur and nitrogen oxide emissions, of course, important for acid rain. But then expanded its scope somewhat. So you can see in 1991, there was a protocol on volatile organic compound emission reductions, which was, of course, focused on VOCs as a precursor of ground level ozone. And then since then, it's gone on to include protocols on heavy metals and persistent organic pollutants, which also include an atmospheric transport pathway. And the most recent protocol under the convention is the Gothenburg Protocol in 1999, which sort of wraps many of these different kinds of pollutants into a single multi-pollutant, multi-effect protocol. Next, please. Yeah, so the Gothenburg Protocol, like I mentioned, the multi-pollutant, multi-effect protocol, has several elements, including national emission ceilings calculated using integrated assessment models, which are basically designed to simultaneously optimize a number of different pollutants and their effects. So in the original 1999 Gothenburg Protocol, the integrated assessment models optimized for the critical loads of acidity in ecosystems, critical loads of eutrophication through the deposition of reactive nitrogen to ecosystems, the ozone effects on human health, represented through the metric of AOT 60, the accumulated ozone threshold, ozone above a threshold of 60 parts per billion, and ozone effects on vegetation with the AOT 40 metric. And so it optimized for all of these things at once. It's not looking just at ozone, but in a holistic way at all of these different kinds of the impacts of air pollution on human and ecosystem health. But it achieved peak reduction reductions in peak ozone concentrations through emission reductions of the oxides of nitrogen and the volatile organic compounds, notably excluding methane in the case of the 1999 Gothenburg Protocol. Next, please. So, yeah, here is a graph of the trends in background ozone. So like I mentioned, the protocol's been fairly successful at reducing peak ozone, but a lot of the ozone that we see in Europe is actually there from the background ozone transported over long distances. And we can see that the declining precursor emissions in Europe and North America did not lead to decreased background ozone concentrations. So by about 2000, it was very clear that a growing proportion of air pollution was due to long-range intercontinental transport. Next, please. And so for this reason, in 2004, the Convention on Long-Range Transboundary Air Pollution created the Task Force on Hemispheric Transport of Air Pollution, TFHTAP, or sometimes just HTAP. Next, please. So yeah, what's the TFHTAP all about? Well, its mission is to foster international scientific cooperation to improve understanding of the intercontinental transport of air pollution across the Northern Hemisphere, specifically with a focus on the UNECE region, given the geographical scope of the Air Convention. So what we do, the overarching questions are, how do changes in emissions in one part of the world affect air quality in other parts of the world? And in any given region, how do the extra regional emissions affect human and ecosystem health within that region? So primarily what we do is we summarize and present the available scientific literature to the convention. This is developing all the time, and it's our job to report to the convention on what's going on. And where we see knowledge gaps in the literature, we organize our own international multi-model assessment studies to fill these knowledge gaps. Next slide, please. So as an example of how we do that, what we do when we organize these international multi-modeling exercises, we take an ensemble of global chemical transport models. So this is a volunteer effort. We don't supply any funding to any of the groups contributing to this. They do this on their own resources. Typically, we end up with something like about a dozen chemical transport models contributing to these exercises. So we get a reasonably good ensemble of models. And we run perturbation experiments with these models to derive source-receptor relationships over a standard reference period. And so what we do is, you can see here on the figure, we reduce emissions systematically by 20% in each of the source regions that you can see, and look at the response of air quality everywhere else. And using this, we can build up a matrix of source-receptor relationships and use this matrix as an emulator for rapid assessment of many different scenarios. Next, please. And so this is just an example of what the source receptor relationships look like for ozone from the first phase of HTAP, the first multi-model study we did in 2010, or that we published in 2010. And so you can see on the left-hand side there, the y-axis, the source regions, North America, Europe, South Asia, and East Asia. And across the top there, the receptor regions, North America, Europe, South Asia, East Asia, and the Arctic again. And you can see the response of ozone as a seasonal cycle in each of these receptor regions to this emission change in each of the source regions. And yes, clearly the response is greatest in the source region itself, but we also see a significant downwind effect of emission changes in each of these source regions. And so using this, we can understand the intercontinental transport of ozone. And it's important also here to point out that you can see quite a large spread in these results. Each individual model calculates a slightly different response of ozone. All of the models have their own individual problems. So we take an ensemble of models to try and get a better estimate of the response of ozone in the receptor regions. Next, please. And so this is an example of what the Task Force on Hemispheric Transport contributed to the last revision of the last review of the Gothenburg Protocol, which we submitted in 2021. So you can see the annual average surface ozone concentrations in Europe from an ensemble of 14 chemical transport models. On the left, the current legislation scenario. There's two different scenarios from 2010 to 2050, current legislation on the left, and maximum technical feasible reduction of emissions on the right. Under the current legislation scenario, we see actually not much change in ozone. Ozone is more or less doing the same thing, despite pretty strong local reductions in precursors from Europe. That's the blue line there under local. So current legislation included reductions of NOx and VOCs in Europe, but we can see that the remote regions were not as ambitious in their current stated legislation, and that the projected rising trend in global methane led to basically an offset of the local effects of reduced NOx and VOC precursors. Under the maximum technical feasible reduction scenario, which included the maximum technical reductions everywhere, we can see that ozone goes down significantly, but only because of the compounding effects of the local precursor reductions, the remote precursor reductions, and the methane reductions. So without these reductions in global methane, the models would tell us that the ozone reductions could potentially be offset by about 1/2. So we see the importance of global methane concentrations for background ozone here. Next, please. Yeah, and again, the significant intermodal spread, showing us the importance of using an ensemble of models rather than just relying on a single model here. Next, please. So just a few words on methane. So like I mentioned earlier, the Gothenburg Protocol in 1999 included emission reductions for SO2, NOx, ammonia, and non-methane VOCs. It was revised in 2012 with additional emission reduction commitments on PM 2.5. The most recent review identified methane as an ozone precursor. The current revision of the Gothenburg Protocol was launched a year later than that, so 2023. And as a response to that, the Task Force on Hemispheric Transport is organizing another multi-model exercise with a focus on methane this time, but also, of course, the NOx and NMVOC precursors to help try and support the ongoing negotiations of exactly how methane should be included in the revised Gothenburg Protocol. So there are several ways that could happen. It could simply be an adjustment of the language in the protocol to mention methane as an ozone precursor, so without any kind of emission limits. It could be an adoption of the Global Methane Pledge by the convention itself, or strongly recommending that parties to the convention adopt the Global Methane Pledge. Most of them have, but many could still do that. Or as an outside chance, there could potentially be meaningful emission reduction commitments for methane in the UNECE region. That's still all subject of negotiation. Next, please. But yes, you can see that methane is now being considered as an ozone precursor, moving from climate policy into air quality policy. There's some interesting demarcation issues there, but it's being recognized more that methane is an important ozone precursor and needs to at least be discussed when we're talking about ground level ozone. Next, please.
3 minutes left, please.
Okay, so what's happening in the current revision? So ozone is not being included in optimizations. Like I mentioned for the 1999 protocol, ozone was optimized in the integrated assessment models. This time that's not happening, and there are various reasons for that. So there were deficiencies identified with the concentration-based metrics for vegetation impacts. It's actually much more scientifically robust to use flux-based metrics rather than concentration-based metrics. It's been discovered that the human health impacts strongly depend on the choice of metric for human health impacts. And we see also that background ozone is strongly influenced by emissions outside the UNECE region. So ozone effects in the revised Gothenburg Protocol will be calculated ex post. And I'd like to just show a couple of examples of how that works in the next 2 slides, for which I'd like to thank Zig Clermont from the Center for Integrated Assessment Modeling. Next, please. So this is what I mean when I said that the ozone impacts are strongly dependent on the metrics. So on the left, you can see the ozone concentrations over UNECE Europe in 2015, in 2014 under a baseline scenario, and 2040 under a baseline scenario for the annual mean MDA8 ozone. This is a long-term health impact metric, and you can see that there's very little change. This is because the emission reductions in Europe alone are not capable of moving the needle very much on this metric. If we look, however, on the right-hand side, we can see the SOMO 35 metric, which shows a lot more sensitivity to ozone precursor emission reductions in Europe. So what we're seeing here is the effects on peak ozone in Europe rather than the annual average MDA8. And next slide, please. So what this means for the combined mortality of PM 2.5 and ozone, if we were to optimize for both of them, you can see that going from 2015 to 2040 on the left, but with the PM 2.5 health impacts in blue and the ozone health impacts in red. If we look at just PM 2.5, we can see a significant reduction of the total health impacts. If we look at if we add the red bars to that, then we see that the health impacts from ozone actually increase slightly due to the impacts of population aging on the health impacts of ozone, and it makes for an overall percentage-wise smaller reduction in the health impacts. If we look on the right-hand side, this is then using the SOMA 35, the short-term exposure metric. We can see a similar story, but also what really stands out is that the ozone health impacts are far less than the PM 2.5 health impacts. And so this is why one of the decisions has been made to do the PM 2.5 optimization, also because there's a lot of methodological uncertainty still in understanding the ozone health impacts. Next slide, please. So what's the outlook? So ozone impact reductions are not being targeted specifically in the Gothenburg Protocol revision. The ozone impacts will be assessed under the proposed emission reductions in an ex post way. So we'll, after doing the optimization for PM 2.5 and ecosystem impacts of nitrogen and acidity, we will look at the ozone impacts, but they won't be included in the optimization. But we do expect that ozone precursor emissions will be reduced through reductions in PM 2.5, acidification and eutrophication, because the precursors of ozone are also controlled by these measures as well. But we know as well that background ozone in the UNECE will still remain strongly influenced by remote sources, probably even more so as the peak ozone concentrations continue to come down. Methane is likely to be included somehow in the next Gothenburg Protocol, but it's still not clear how. And HTAP, the Task Force on Hemispheric Transport, is organizing another round of multi-model experiments to understand the long-range contributions to ozone in the UNECE region to support this ongoing revision process. Thank you very much.
Thank you, Dr. Timothy. Bueno, pues ahora pasaremos a la
At this
sesión
time,
de preguntas y
we will
respuestas,
be going to the
donde
Q&A
les
session.
pediremos, por favor,
And
que
here,
hagan preguntas
we will
concisas y
ask you
breves
to
para
ask
poder darle la
brief,
oportunidad a las
concise
personas que
questions
participen.
to give an opportunity for more people to
Bueno,
participate.
vamos a tener aquí una lista de
And
preguntas.
we have a
Como
list of
comentaba
questions.
Ramiro en el
As
chat,
Ramiro
Dr. Sang,
mentioned
por la
on the
diferencia
chat,
de horas, pues ya
due
no están
to
presentes.
our
De cualquier manera, le haremos
time
llegar las
difference,
preguntas
Dr.
que nos ha
Shang,
hecho aquí
who
el
is
doctor
not
Ricardo
present at the
Torres,
meeting,
quien
we
pregunta
will
qué
let
tan
her have
importantes
the
han sido
questions, like the one of Dr. Ricardo
qué tan
Torres.
importantes han
How
resultado los compuestos
important
carbonilos,
have been
formaldehídos,
carbonyl
en la producción de
compounds
ozón
like
en China?
formaldehyde and ozone
La doctora
formation in China?
Georgina
Dr.
pregunta que
Georgina
cuáles fueron
Pellicer
las
is
medidas
asking,
concretas
what were the
implementadas que
concrete
permitieron
measures
la
implemented
reducción de
that
CO2 en el
enabled
corto
to
plazo y
reduce
las
COCs
NOxes en largo
in the
plazo
short term and then
y que en conjunto
NOxes
lograron
in
una
the long
reducción
term, and
efectiva
together
del ozono?
bringing about an effective reduction of
Por
ozone?
otra parte,
On the other
pregunta para la
hand,
doctora Laura
there is a
Gallardo.
question
La
for
pregunta
Dr.
es de
Laura
Elizabeth del
Gallardo,
Carmen, quien
question from
pregunta, a
Elizabeth
nivel
del
global,
Carmen, who's
¿cuál es
asking,
el impacto de los
globally,
incendios
what is the
forestales de gran
impact of
magnitud que se han
massive
presentado en los últimos años?
wildfires in the last
Adelante,
few
doctora.
years? Doctor, over to you.
Doctora Gallardo.
Dr. Gallardo?
En general,
Well, in general terms, the impact of biomass being burnt is substantive, both in terms of underlying ozone. Burning biomass is important, and this biomass burning is definitely bringing ozone precursors. And now, in the context of wildfires, which we see more and more intense in many parts of the world, that definitely increases this contribution we knew even before burning biomass. And yes, that is something we need to be able to quantify, but quantifying it is not easy because of the non-linearity of hydrogen, and there is a big impact associated to the wildfire itself. And it also things change like radiation, actinide flows, and it depends on the combination of what is being burned at what temperature, etc. And therefore, it is not an easy thing to quantify at the global scale, because you also have non-linearity in regional characteristics, which might be a little bit different, but I am certain there should be studies being conducted. We are behind in the agenda, so some of the questions have been responded over the chat, and the ones that have not been responded, we will be sending them to our presenters. Thank you, and with this, we're closing the first session.
Adelante, Ramiro.
Ramiro, over to you. Thank you. Due to time constraints, we will now kick off with the second session. I would like to thank Dr. Elizabeth Vega